with a single variable optimization. Single variable optimization. Single variable, that means only one variable involved. We have function of fx. Here x represent the variable. So this is the single variable. When in case of multivariable, that means we use the function in this form: f of xy, two variables, three variables, f of xy, z. So we define as a function of one variable fx is said to have a relative or local minimum at a particular point. We consider as at x equal to x naught or x equal to x star. So we consider as x equal to x star. We can assume that at x equal to x naught. So what is the condition for this? That means the condition is that if fx star, the value, if fx star, that means at x equal to x star, this is less than or equal to f x star plus h, h being a positive quantity. We know the definition of a differentiability. We write as f dash x equal to limit h tends to 0, f x plus h minus fx upon h. So we have to remember, because we define in first line, that means we obtain the optimal solution of continuous and differentiable function. So we have to remember that the condition is that for continuity and differentiability, we move to the calculus. So we know one important theorem: a function which is differentiable, that means this also be the continuous function. But a function which is continuous need not necessary to be a differentiable function. So differentiability tends to continuity, but continuity need not tends to the differentiability. So relative or local minimum. Local minimum at x equal to x star, that means function f of x star is less than or equal to fx star plus x. For all, we write as for all sufficiently small positive or negative values. Sufficiently small positive or negative values. Positive or negative values. For what? H. Here we can consider as h is greater than 0, but we can consider as h less than 0. Similarly, for second point, a point x star is called relative or local maximum. Relative or local maximum if fx star which is greater than is equal to fx star plus h for all value of h. For all value of h which is sufficiently close to 0, sufficiently close to 0. So there are two conditions. First is fx star which is less than equal to fx star plus h, or second is fx star is greater than fx star plus h. For local minimum, this condition is satisfied, and for local maxima, that means fx star which is greater than. So you keep in the mind the definition of differentiability. So on the basis of definition of differentiability, we are writing these two statements. That means this statement and this statement. You have we have a limit h tends to 0. That means derivative of x, f of x plus h minus fx upon h. Here in place of h we write as h star at x equal to x star. So in the numerator, so we write the numerator value. That means if fx, that means this value fx which is less than to this value fx star plus h, depend upon the value of h. Similarly, fx star which is greater than fx star plus h gives us the local maximum. Noted? Manship Nakshi, you noted this? Okay. Vibha? Okay, good. Yes, friends, kindly note down all the lectures. Now, if function, we write if function fx is said to be global or absolute minimum. Global or absolute minimum at x equal to x star at the value, that means x equal to we consider as x star if fx, the value of fx star is less than equal to fx. So for global minimum, we have this condition at x equal to x star if fx star is less than equal to fx. So we can represent by the shape for different level. That means what is the local minimum, global minimum. So you can understand this. So we draw a graph. This is x and here fx. Origin, we start with x naught. That means we can take x equal to a. Here x1, x2, x3 and so on, or this is last point is xn. Here we denote it as b. Xn equal to b. This is x, you can write as x naught. That means we take the interval a to b. So our shape, approximately we can draw a shape. So we construct a shape. What is, so this is the lower limit. We write as this is lower limit, this is upper limit, this is upper limit, and this is local maximum. This is local maxima. This is local maximum. How to write local maximum? We can check as second derivative which is less than 0. Local maximum. This is for local minima. This here we write as local minima. For local minima, that means f double dash x. F double dash x is greater than 0. That means for positive f. Here this is for local minima. Here we write some points, gives us point of inflection. Neither minima nor maxima. Sometimes you can shape this side. So here we write as f double dash x equal to 0. And this is the global maxima. That means maximum point of the curve. Global maxima. Global maxima, or this is the global minima. This is the global minima. So we have any function fx. According to fx, we draw a curve. So we write all the points. We denote it as this is the lower point denoted as a, and this is the upper point denoted as b, and write all the points. So you totally understand about the differential calculus, because these are the points we are discussing here related to the differential calculus. In differential calculus, we find out the maxima minima for single variable. So what are the conditions for calculating maxima or minima? So we know that fx, function fx is given. We find out the first derivative. We put a first derivative equal to 0. That means obtain the stationary point, stationary value. Then we obtain the second derivative. And after obtaining second derivative, we put the stationary value in the second derivative. We have to check if second derivative less than 0. So we say that the function is maximum, or greater than 0, we say that the minimum. And we put the value, stationary value in the function, we calculate the value of the function. In third case, if f double dash s equal to 0, so we can say that neither maxima nor minima, or we can say that further investigation are required. So we again determine the third derivative and fourth derivative. So same procedure we have to follow here. We are talking about the single variable optimization. So we have to understand that what is the local minima, local maxima, and global minima, global maxima. So there are 2 points you can see and or you can understand this. These are 2 points here which are in increasing side. The first point, this is less peak height to this point, that means this point. So we give this as a local maxima, and this is much peak height, means maximum peak height. There is no other point. So this is the global maxima. Similarly, for lower side, so this is the local minima or this is the global minima. Local and global. Local maxima, local minima, global minimum, global maximum. Global maxima or global minima of a function over the large interval can also occur at the endpoints, which may be also occur at the endpoints. This is not necessarily will occur on the middle of the curve. Okay, noted. So theoretically, we can write as a single variable optimization problem is one in which x equal to x squared to be found in the interval. This is the interval we write as a to b, find in the interval a to b, such that x star, that means we some book authors can use x naught or some are using x star. So x star minimize the fx. So on the basis of that, we have one theorem for necessary condition and one for sufficient condition. So we have to solve necessary condition theorem. Okay. So necessary theorem for necessary conditions. Necessary condition. If a function fx statement if a function fx is defined in the interval a less than x less than equal to b and has a relative minimum at x equal to x star, where a is less than equal to x star to b, that means lie between inside, and if the derivative d of fx upon dx equal to f dash x exists as a finite finite number at x equal to x star, then f dash x star is equal to 0. You can understand the statement. That means a function fx is defined in the interval is closed interval a to b, x lie between a to b, has a relative minimum. That means we defined as fx star is less than equal to fx star plus h, relative minimum at x equal to x star, where x star lie between a to b, that means open interval. Here we are talking about the closed interval, here we are talking about the open interval. So and if the derivative of fx, function fx with respect to x, we write as f dash x, exists as a finite number at x equal to x star. So we can say that the derivative at x equal to x star equal to 0. So we have to prove this theorem. So we can consider as it is given that f dash of x star equal to limit h tends to 0 f x star plus h minus f x star upon h. This is the equation number 1. So we have consider that if a derivative exists, so that means we have the definition of differentiability or derivative. That means f dash x star, which equal to limit h tends to 0 fx star plus h minus fx star upon h. So we can draw a graph. This is for x, this is for fx, function fx. Suppose we are considering this type of graph. Here this is the interval a, initial interval, and this is the b, and the point at this surface is a. Here the point is b, we write as b1, and this point is a2, and this point is b2, and here the point is a3. This point is a3. So what we mean by a relative maxima? That means these 3 points a1, a2, or a3. So we can write as a1, a2, and a3. These 3 points represent the relative maxima. Relative maxima. And the point a2 is bigger than a1 and a3. So this point is known as the global maxima. This is the global maxima. We write as global maximum. And the point b1 and b2, they are known as the relative minimum. And the point here is b1. b1 we write as global minimum. Dear students, you have understand all these topics. That means questions can be asked related to low relative maxima. What do you mean by relative maxima? Global minima and local minima, local maxima, global minima. So this is shows the relative and global minima. So this is the relative minima and global minima, or we can say the relative maxima or global maxima. Now we move here. It is given that means if this f dash x, if derivative is exists, so then we move further. Yeah, noted students. Mansi, Nakshi, Shifali. Okay. Okay, good. So we write as f dash x. So equation 1, that means exists as a definite number. So we want to prove x star prove to be 0 since x star is a relative minimum. So when x star is a relative minimum, so we can write as f x star, which is less than equal to f x star plus h. F x star plus h for all value of h. We write in the for all value of h. Sufficiently close to 0. So if f x star less than equal to f x star plus h, we can write as f x star plus h minus f x star upon h. That means this value f x star is less than 0. Obviously, this value gives us greater than 0. If h greater than 0, that means if h is positive, so that means the value of fx star plus h minus fx star upon h is greater than 0, and f x star plus h minus fx star upon h is less than equal to 0. Here f h is less than 0. So this gives us less than 0. So from the equation number 1, from equation number 1 gives the limit h tends to 0. H tends to 0 through positive value. When this gives the positive value, that means f dash of x star greater than equal to 0 from this condition. And for a negative value, when it gives the limit as h tends to 0 through negative value, so this means the LHS part f dash x star is less than equal to 0. So this is the equation number 2. We can give the equation number 2 here. Then this is the equation number 3. So there is only one way. That means first for positive value f dash x star is greater than equal to 0. Second, for negative value f dash x star is less than equal to 0. So there is only the way which satisfy both equations, equation 2 and 3, which is f dash x star equal to 0. So the statement was that the derivative exists at finite number of x equal to x star, then f dash x star equal to 0. So here we are saying that f dash x star is greater than equal to 0. Here we are talking about f dash star is less than equal to 0. So when we satisfy equation 2 and 3, then we conclude that f dash x star equal to 0. So we have to prove this theorem. We write here. From equation number 2 and 3. The only way to satisfy both equations, which is f dash x star equal to 0. So this is the proof of the theorem. Here we prove this theorem for a relative minimum. We can also prove this theorem as a relative maximum. That means x star taken as a relative maximum. So we can similarly prove this theorem. Noted? Bhavna, Manshi. Okay. Okay. Now we discuss next, that means convex and concave function. Convex and concave. So first we write a single variable function a single variable function which when plotted the result in a curve always curving downwards. Curving downwards, or not curving at all, or not curving at all is called concave function, is called concave function. That means curving downward or not curving at all. That means flattened. So such type of function is known as the concave function. This can be, we can write, it can be shown for a concave function of several variables, that it has a local maximum. It has a local maximum. So you understand the points local maximum and a local minimum and a global maximum. The same is also a global maximum. Same as also global maximum. So in numerically we define as a function fx is said to be concave over a region S if for any 2 points, x and y in S, give as f function of lambda x plus 1 minus lambda y, which is greater than or equal to lambda of fx plus 1 minus lambda of fy. Here lambda lie between 0 to 1. So numerically we define for 2 points. 2 points considered as x and y. And we draw the concave function for 2 points x and y. That means you can understand here. That means this is x, or you can give as capital X, and here we write as fx. And 2 points, first we consider as x and second we consider as y. So we draw these 2 points, and we this point, and we take the curve in this way. So here this represents the f of lambda x plus 1 minus lambda into y. So this shows the concave function. This curve shows the concave function. Concave function. That means curving downward. Curving downward. This is shows the curving downward. So this is function fx. That means f of lambda x plus 1 minus lambda y. Here 2 points we consider as x and y. Similarly, we define for convex function, which is